If the static coefficient of friction is 0.500 for this situation pictured here, what is the steepest incline where the box would not slide? So we're going to approach this as a force problem. I mean, that kind of makes sense, I think. So what should we start with? I think we should start with an FBD. Probably we already have a sketch there, so I think I'm just going to start with an FBD and sort of see what happens here. And I always like to start with that force of gravity, so I'm going to start there. I think there has to be a normal force. We've done one like this before in the past. I think we've done a couple. We've done both without friction. We've done it with friction. I think in the past we were given friction, but now we're only given that coefficient, so that's going to change things a little bit. If it's not going to slide, it means that clearly there must be a force of friction preventing that. It's probably not huge here. I'm kind of guessing a little bit there. Sometimes my free body diagrams are not perfect. They may get better as I understand the problem more, though, in some cases. So what do I do next? I've got those three forces. What do I do with them? Well, we're being asked for the steepest incline. So one thing I might notice to say, well, I'd like to maybe somehow get an answer for some kind of angle, right? So like if there's some angle associated with this incline, I'd like to know what it is. That starts to help me thinking about what I could do here. The other clue, I think, when I read this question through again, is that it's talking about the steepest incline where the box would not slide. So if it's not sliding, I think it means, and the fact that we're given static coefficient of friction kind of implies that this thing's not moving. So I think we're looking at a situation here. It's static. It's not accelerated motion. It's, so in other words, I think the net force must be equal to 0. So I'm going to write that down kind of as a clue as to how to proceed with this. And you might remember that once you made a decision like this, now typically in a force problem, the next choice would be things like, well, what coordinate system am I going to use? Am I going to do a geometric analysis instead? Or am I going to do components? Well, let's explore this a little bit here, right? In case anyone forgets that. Maybe some of us might look at this and say, oh, I think I see what to do next here, right? I think I know what the next choice would have to be. But what might help me if I wasn't sure, and if we're still not sure, I don't know, are we sure? Anyways, I'm writing down explicitly, not necessarily neatly, but explicitly, the three forces that are in my picture and saying those must add to 0. And recall that a vector equation, like if we're going to do components, we're going to do algebra, right? If we're going to do geometry, we're going to draw a picture. And when do we usually think a picture would be nice to draw? Well, typically if it's a nice simple right triangle, that's when things turn out really neat, right? And this question saying the angle equals, we're trying to find the angle, wouldn't it be cool if a right triangle came out of this? And I think it might, because the force of friction and the normal force are in fact at right angles. So if I kind of like, if I redraw this picture, the one I drew up there, and then at some point I'll have to figure out where the angle is, of course. But, I'm starting with force of gravity here. I kind of just start arbitrarily. Normal force maybe off at some angle. I don't know if I'm being exactly, oops, I made it a little bit long there. So maybe this is something that might happen to you too, is like you actually make something a little bit long. Well, I'm just going to make gravity a little bit longer here. Because I know that the force of friction, I'm supposed to kind of go back to that spot on. Why do I have to return to that spot? Well, we're saying the vector sum of these three forces is equal to 0. So head to tail, Fg plus Fn plus Ff must return you to 0. So clearly, if I look at this kind of from a right triangle perspective, I would say, so let me just redraw it without the arrow so I can maybe think about it as a triangle more easily. I'm looking at this kind of a situation. Fn and Ff comprise the two legs of this right triangle, and F sub g really is the hypotenuse of this kind of like force triangle we have now. What do you bet that angle theta might be here? And how do I know that might be the angle theta that I'm after? Well, the simple trick that I prefer is to recognize the way I've drawn things here. I kind of reflected the fact that this incline is not that, hugely inclined. And so it makes sense that since this is kind of a smaller angle, that maybe if I did things carefully, this would be a smaller angle. And I was pretty careful here. Maybe not perfect, but I think I was careful enough to make that assertion. You might recall in the past that we've gone through and kind of analyzed the angle of the normal force relative to the vertical, and then kind of traced that through these pictures and found that conclusion tended to hold. So you can go back and look at some earlier videos if you wanted to see examples of that. But what this means here is that I could start to think about like what kind of like trigonometry would I like to use to get an answer, right? Well, something that might help me figure that out is the fact that since we're talking about static friction, we know that the static friction rule in general is force of friction is less than or equal to coefficient of static friction times normal force. Now, an inequality is not terribly helpful, but since we're talking about the steepest incline, I'm going to argue that right at that moment where it's the steepest it could possibly get, this won't be an inequality, but the force of friction will be as large as it can possibly be. And so based on that argument, I'm going to erase this inequality here and change that to an equal sign. And okay, that's pretty cool. In fact, one thing I can maybe do with that is, you might wonder why am I doing this, but I like ratios. And I'm just going to solve for the static coefficient of friction and say, hey, the static coefficient of friction from another perspective is really just the ratio of the friction force to the normal force. What else might have that ratio? Well, the tangent of theta in this triangle is equal to opposite over adjacent, which is the same ratio in this case. That means that, let me just kind of go over here because I'm running a little low here. But that means tangent of the angle I'm looking for is equal to that coefficient of static friction, which we have a number for, right? That's that thing we were told is equal to a half, or at 3 sig figs, a half, right? But I'm just going to write 0.5. I can't remember if I mentioned this in the previous, in the introduction to this topic, but coefficients of friction generally don't have units. So you don't have to ask, like, is this centimeters, meters? No, they're just pure numbers. But this means I can solve for that angle by just taking the tangent inverse of the coefficient of static friction, which really means in my calculator I'm going to want to take tangent inverse of a half. And so now I go and run to my calculator and put that in. And in degrees, it gives the answer of 26.56505, etc. But I think we'll go with 3 sig figs here and round that off to 26.6 since we were really just given that 3 significant figure coefficient of friction. I still doubt the validity of that, but in case a chemist gets hold of this video, oh shoot, they just heard me mention them. But anyways, at least they know we're following their rules, yes? So there it is. It looks like we got it correct at that level of certainty.